In this video lecture, we're going to give an overview of quadratic programming, and it will include an example of how to define, formulate, and solve a quadratic program. So a quadratic program is an example of an optimization problem that just takes on a particular form. So a quadratic program specifically has a quadratic objective function, meaning that it'll have our decision variable squared terms in there, and it has linear constraints. So the QP solver in MATLAB is a function called quadprog, and it uses the formulation shown below. So our objective function has to be in this form. We're going to minimize 1/2 times x transpose, where x is a vector of our decision variables, times h. So h contains the constant coefficients that are going to multiply the squared terms and the x1 times x2 terms. And so to get those x1 squared and x2 squared terms, we have to multiply this h 2 times by that column vector x. Then we have the linear terms in our model. The coefficients go into this vector called f, so we have f1 and f2 that are going to multiply to define the constant coefficients on the purely linear terms. And again, this 1/2 is just sort of a nuance of the solver, so we need to be very careful with that 1/2 later on when we're formulating this problem, that we make sure that the scalar version of the objective function that we write down will correspond exactly to the matrix version. This will all be much more clear once we actually define a problem and solve it. Our constraints need to be in this form, so we need to define a vector that's the same size as x. That vector will be called LB, and that will contain the lower bound for each of our decision variables. Similarly, this vector called UB will define the upper bound. If we have equality constraints, we'll need to define them. Remember, these are all linear, so we can do this all with matrix algebra. We'll need to define our linear constraints in this matrix A sub EQ and in this vector B sub EQ. So just to clarify what those are, the matrix A sub EQ is a matrix that has as many rows as you have equality constraints, and it has as many columns as you have decision variables. The B sub EQ vector has as many entries as you have equality constraints. So as many rows as you have equality constraints, but it's only one column. It's a vector. Similarly, for our inequality constraints, so this is for equality constraints, and this is for our inequality constraints. So the A matrix has as many rows as we have inequality constraints, and it has as many columns as we have decision variables. The B vector has as many entries, as many rows as we have inequality constraints, but it's a single column, so it's a column vector. So again, this sounds a little bit obscure right now, but this will make more sense once we define an actual problem. So here's an example problem. So a manufacturer has done empirical modeling of their production system and has determined that their production cost is determined by this equation. So the cost is equal to 0.4 times x1 squared minus 5 times x1 plus x2 squared minus 6 times x2 plus 50. So here we have, these terms are going to relate to the quadratic part of the objective function. Quadratic. And then these terms are going to relate to the linear. So we're going to put the coefficients here, 0.4 and 1. We're going to build those into our H matrix. And then the 5 and the 6, the linear terms, we're going to build those into our F vector. So in this problem, x1 and x2 are the decision variables. So in this case, the rate at which they should run unit 1 and unit 2. So we want to find the right combination of x1 and x2 that results in minimal cost for this manufacturer. So again, our production cost is given here, and if we're trying to minimize cost, then that makes this equation, cost as a function of x1 and x2, this is our objective function. So it's quadratic because it has only linear and squared terms in it. It could also have bilinear terms, so it could have plus 10 times x1 times x2. That would still be quadratic. But this particular problem doesn't have any of those terms. So the corresponding parts of the H matrix will be zeros because we don't have any of those bilinear or x1 times x2 terms. So if we were to take this objective function, this cost function, and plot it using a contour plot, this is how it looks. So these lines represent, the closer you get to the center, this represents decreasing cost. So just by looking at our objective function, we haven't defined any constraints in the problem. We just say minimize the total cost. So the minimum point is going to be right at the center of this ellipse, right there. And that optimal point, after having solved this in a QP solver, our QP solver gives us this point. So our optimal point designated by the stars, x1 is equal to 6.25, and x2 is equal to 3. So that's our optimal point when we have no constraints in our system. And the total cost, which is evaluated just by plugging in our optimal x1 and x2 into our cost equation, that optimal cost was 25.4. So we'll go through how to formulate this and solve it in a QP solver. Right now I'm just showing you graphically what this problem looks like. So a quadratic program, this one looks quite nice, and you can see that it's pretty easy to tell where the optimal point is just graphically. So what happens when we add an inequality constraint? How does that look? We have the same objective function, but now we're requiring that x2 minus x1 be greater than or equal to 2. How does that change this problem? So now I've plotted that equality constraint. So actually we have, x2 minus x1 has to be greater than or equal to 2. So this line represents x1 minus x2 being equal to 2, but we have to be greater, so we have to be on this side of the line, which rules out any of this space. So this space is called the infeasible region. So you notice that our optimal point previously was right about here, and now that's no longer in our feasible region, so now we have to find a new optimal point that's in the feasible region. So that optimal point, just graphically, if we're decreasing in our costs in this direction, our optimal point is going to be right there. And again, these are the results of having solved this problem using MATLAB's QP solver. So our new optimal point is x1 is equal to 2.5, x2 is equal to 4.5, and our cost is now 33.25. So you notice our cost is now higher. Adding in this constraint means we have less flexibility and less room to find an optimal point, so our objective function gets worse. And generally that's the case. By giving our system more constraints, we typically will find, we can never find a better optimal solution. We'll typically find the same or worse. And in this case we found a worse optimal solution as we've moved from our previous optimum to our new optimum. So let's add in another constraint. So in addition to this constraint, we now have this new constraint. 0.3 times x1 plus x2 has to be greater than or equal to 8. And we've also put on input constraints. So we're saying that x1 and x2 both have to be between 0 and 10. So let's show the plot. So the objective function looks the same. And now we had, this region was ruled out as infeasible based on our last constraint. This is our new constraint line, and we're saying that we have to be greater than that line. So this is going to be the feasible region now. And we've ruled out this region as being infeasible. We also added input constraints where x1 and x2 have to be greater than 0 and less than 10. So that actually corresponds to the region that's outside of this graph. So now our feasible region is just this tiny little section shown right here, and a quadratic program can help us still find the optimal point. And it's fairly easy just graphically. We're seeing decreasing costs going in this direction. So we think our optimal point is going to be right there. So this new optimal point is x1 is equal to 4.62, x2 is equal to 6.62, and our cost is 39.5. So again, we got a little bit worse on the cost because we have a more constrained system. So previously I've just shown graphically what this problem looks like and what points we're actually trying to solve for. And it's important to get a pretty good visual of what your objective function looks like and what you're actually going for in the problem. But that's only possible when you have a few enough decision variables that you can put it on a plot that still makes sense to human eyes. So we had two input variables, which gave us basically a three-dimensional plot once we added in our objective function. And that's pretty much the limit of what we can do graphically. But we understand the basic concept of quadratic programming using that simple two-dimensional example. So if we look at the scalar formulation of our of our QP, our optimization problem, we're trying to minimize the cost given here, and we have these constraints. So these are both inequality constraints. The problem does not have any equality constraints. So we don't even have to worry about adding in equality constraints. And then here we have our input constraints, or our decision variable constraints. So this is our problem. So now the trick here is to take this problem and get this into the matrix form that our QP solver requires. So it's simple enough to define it in the scalar form, but our solver basically can't work with it in this form, so we need to transform it into the syntax that our solver wants. So first of all, if you'll remember, the basic formulation required that our inequality constraints have this less than term. So actually, the way our problem is formulated, these are both greater than constraints. So we need to flip those around and make them less than or equal to constraints. And we need to get it into this matrix form. So to get these to be less than or equal to constraints, we multiply each side by -1, and then we flip the sign. So now instead of x2 minus x1 has to be greater than or equal to 2, we now have x1 minus x2 has to be less than or equal to -2. And similarly for this constraint, we have minus 3/10 times x1 minus x2 has to be less than or equal to -8. So these are equivalent, but we have to put it in this form where we're only using this less than or equal to constraint. So we're trying to go from this scalar form to this matrix form. So we do that carefully so we can define our H matrix. We take these coefficients, so 0.4, and then there's a coefficient of 1 in here, and we put them into this H matrix. So there's a little trick here. Remember that our QP solver is going to require this to be in this form, so it's going to automatically take half of whatever we put in. So we need to double our the constants in our H matrix in order to get it in that form. And this is just an artifact of this particular solver that we're using. Not all of them will use this, but we're using MATLAB's quadprog. So if you typed in help quadprog in MATLAB, you would see this same matrix form that we need to get our problem into. So this is what our H matrix looks like. This is what our F vector looks like. So we're just taking the -5 and the -6 here and plugging those into a vector. So now we need to do the same with our inequality constraints. So we have two inequality constraints, which gives us 2 rows here. And then we have 2 inputs, so that gives us the 2 columns here. And we're just taking the coefficients from these inequality constraints and plugging them into this matrix. So there's a 1 here, there's a -1 here, 1. So you see 1, -1. There's a -0.3 here, and there's a -1 here. And now we take our B column vector and we put in these constant terms into that B column vector. So if you were to take this matrix times x and do the matrix multiplication, you would end up getting these same these same constraints in the same basic problem. So we also need to input our upper bound and our lower bound. So x1 and x2 both had a lower bound of 0 and an upper bound of 10. So we set up our LB vector with zeros and our UB vector with 10s. So that defines our input constraints on our system. So now the biggest trick is to just code this into MATLAB and feed this into the quadprog function in MATLAB. One thing I forgot to mention was, because we don't have any equality constraints, those are just going to be the matrices that correspond to those equality constraints are going to be just empty matrices, which the solver might actually require you to enter. We're just telling it there are no equality constraints in this problem. Another important thing to mention is that we had this other constant term of 50, so our cost has this constant term, but you'll see that that 50 doesn't show up anywhere in our problem formulation. So because it's a constant term, it doesn't affect where the minimum is, it just affects what is the value of that minimum. So when we solve this problem, the quadprog function is going to spit out the optimum values of x1 and x2 that minimize this function, but it won't actually tell us what our cost is. We'd have to add this 50 back into that solution to know what our minimal cost is. So we've done all this graphically, and I've tried to make this problem as simple as possible so that you can understand what we're going for here. But you might ask, well, if you can just graph this problem, why do you even need to solve it using a quadratic programming solver? So here's my explanation. So the problems can get very large. You might have thousands of variables and constraints, which means you can no longer graph this thing. Our problem has 2 dimensions, and then our objective function is plotted in the 3rd dimension. So it's easy enough to plot a 2-dimensional problem, but once you start getting bigger and bigger problems, you can't plot it anymore. So plotting really doesn't do you any good. So when you have more than 2 independent or decision variables, the contour plots are no longer possible. You might need to get answers very quickly, so you might need to just solve this and have the computer doing this behind the scenes. So the graphical method also requires a human to look at those plots and to determine where the optimal point is on there. Where we really want to automate this whole process and have a computer be solving for the optimal points and telling us what the answers are. So this is very important in real-time optimization, as is the fact that the problem can change over time. So those coefficients that showed up in our objective function, those might change from time to time. Maybe the cost of buying material A changes. That changes your problem fundamentally, so you need to have a way of adapting your QP, or your optimization problem, to take in that new information and resolve. So if costs of materials change, or if environmental conditions change, or if something in the system itself changes, then our optimization problem changes and we'll need to resolve it. So there are a lot of reasons why you'd want to actually solve this mathematically rather than just trying to graph it and find the solution. And these are just some of those reasons. So in our next video demonstration, we're actually going to show how you formulate this and solve it in MATLAB. So we'll take this same problem and I'll walk you through how to code this and how to get that optimal solution.